All right, everyone, welcome back. Today's the day we put it all together in this chapter, and it's been kind of jumping around a little bit. Hopefully, I've been mentioning that in class also. Not sure if I have or not, since I'm doing this well before we are in chapter 6. In case you're interested, we're still in chapter 5 right now. It's October 2nd. So anyway, this is called the fundamental theorem of calculus. Sounds pretty important, and it is. But it kind of puts the symbol together with area under a curve versus antiderivatives. So this theorem actually has two parts. The first part's not the most important part. We just need the first part in the proof for the second part. We do a couple little example problems of the first part. It's pretty straightforward. But the second part, the first part's going to make more sense later on, but I'm going to introduce it to you right now just to so you see it. The basic idea of the first part, we've kind of done this already with a definite integral. We know that the integral of small f we call big F antiderivative, but if we took the derivative of the antiderivative, we'd be right back where we started. So we've already kind of talked about that a little bit. So we're going to carry that idea through today, even with the what we call the definite integral with limits. So all this says is, what all you need to know, don't worry so much about this. This is part of the proof. I'm going to not even show you the proof. It doesn't really matter. Normally I would if we had a little bit more time, but in lieu of time, not so important. So what you need to kind of know is, I'm going to do a little erasing of this. For the first part is this. Very simple, that the derivative of the integral from a to x of f of t dt equals f of x. It's very similar to this. Some of you would think, well, it's exactly the same thing, except for we got limits on these integrals now, right? So we're now talking about area under a curve. We're not really talking about antiderivative. Now you can see the connection is getting closer, right? Is that clearly the integral symbol, area under curve, has something to do with antiderivative also. I'll give you a couple examples. This is all proof, so I'm just gonna, if you want to see the proof, you can look at the book. But basically, all we're going to do with this, and again, the reason we need it is because it's in the proof of the second part, which I'm not going to prove to you either. But we do a couple examples. So here's just an example, right? The derivative, and so that it's a to x, right? So a is a constant, and x is just x, not 2x or 3x. That's going to be a little bit different, but just x. So here we go again. The derivative from negative pi to x of cosine t dt is just cosine x. Notice the t is getting replaced with that x. Right, and again, when we do the second part of the theorem, and then we practice it a little bit, we'll come back to this and I'll kind of show you a little bit more about why this works. Okay, for now, we're just going to say it works and go from there. But it doesn't have to just be constant and x. So it's possible there could be a function of x up in the top there, like x squared. So now we need the chain rule, okay? Because remember, we are taking a derivative, right? So what's going to happen is there's going to be a chain rule in there. So I try to go through a bunch of processes, but I'm going to kind of skip this and just show you that this is equal to what you think it would be equal to, which is the cosine of x squared, right? Remember that this x is going to get plugged in there for the t. The problem is we still have this chain rule piece of it. And again, this will make more sense in about a week. But you just have to multiply. It's just like the chain rule. So you take like the derivative of what's inside. What's inside of this is that x squared. So we just multiply it by 2x. Pretty straightforward, pretty simple. Here's another example. It can be as complicated as you want. This 3x cubed plus 2x plus 1 is going to wind up in there. So we get secant of 3x cubed plus 2x squared plus 1. And then we have to multiply it by the chain rule, the thing that's inside of it, which is 9x squared plus 4x. We're actually going to extend this idea later on and put variables here also, but that's coming a little bit later. So now this is really all you have to be able to do for now. Just know that this gets used in the second part of the theorem, which is the most important part. So this is the fundamental theorem of calculus, part 2. It puts everything we've done together. Some of you already know this, I think. You've heard this before or seen it before. So what it does is now it connects area under curve. So remember that the integral from a to b of f of x in our definition, now when you put those limits on there, doesn't mean antiderivative, right? This means antiderivative. This means area. But the question we've been kind of talking about all chapter is, why do we use the same symbol? Well, because they're connected. So it turns out that to find the area under the curve, remember, we don't have very many ways to do this. We have to draw a picture or use those rectangles. Again, turns out that to find the area under the curve, you can just take antiderivatives. So all that says is you take the antiderivative of f, and then you plug in b, you plug in a, and you subtract the 2. Okay? We're going to be using this all year long. It's clearly got an important name, right? Fundamental theorem of calculus. I'll show you a bunch of examples right now. Underneath the black, there's a proof. You don't really need the proof. So it just allows us a way to use the antiderivative to find the area under the curve, which is a pretty powerful thing, right? Because all we've been able to do so far is perfect pictures like circles or triangles or trapezoids, or estimate. So this allows us to not have to do either. So here are a bunch of examples. I'm just going to do a bunch. Try not to be too long for you here, and kind of show you some notation also. So again, just to have you remember what this means is this is area under a curve, right? So we got this little area sine curve, 0 to pi. That's what we're looking for, yeah? The math is going to handle this for us, by the way. It's going to treat this like a negative area. It's really cool. If I actually did 0 to 2 pi, the answer would be 0, right? You wouldn't even have to do it. So notation, remember that big F of pi minus big F of 0. So here's some notation for you. You take the antiderivative, which is negative cosine x. And then this is a little notation that you're going to see me use all the time. It's just like a little vertical line or a bracket with those limits on there. This is, remind me, it's negative cosine of pi minus, be careful, this minus sign is part of the formula, and then negative cosine 0. You can get a little hung up sometimes with the negatives. Cosine of pi is negative 1, so that's 1 plus 1, we get 2. And just notice, if I change those limits to 0 to 2 pi, negative cosine of 2 pi minus negative cosine of 0, which is 1. Let me see if I make sure I got that right. Negative cosine, yeah, plus, uh-oh. I make a little mistake there. Let me try that again. Negative cosine of 2 pi. Cosine of 2 pi is 0, is 1. So that's why. Negative 1 plus 1. There we go. I knew it was supposed to be 0. It's just 0. So the math handles that area under the curve for us. We don't have to worry about that. So the trick on these then is, how do you take the antiderivatives, right? So back at the beginning of this chapter, you may remember a long, long time ago, the first thing we did was just practice antiderivatives. So power rules and step one so far. We're going to learn more ways to take antiderivatives ultimately, but right now it's just power rules, some trig ones, inverse trig, exponentials, the ones that we're supposed to know. So this would be a power rule, x to the 4th over 4 plus x from negative 1 to 3. Oh, by the way, some people ask me about the plus c. Remember normally when you take an antiderivative, you do a plus c. I'm come back to that question here in 1 minute. When I'm finished with this, I'll show you why we don't worry about it. So 3, 9, 20, 81 over 4 plus 3. That's plugging in the 3 minus, plug in the negative 1. So you get 1/4 minus 1. I'm going to just stop there. You guys can do the arithmetic. No calculators, by the way. No calculators on these. You might have some fractions and stuff to deal with. 81 over 4 minus 1 over 4 is not too hard. It's 80 over 4. So sometimes you might have to find a common error. So why not the plus c? Well, remember that if there really was a plus c, I'll put it a different color, like plus c, and then you did this, that plus c is going to cancel out, right? That plus c is going to be here, then minus, yada, 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 plus c. So those are going to cancel out. So we just kind of ignore it. It really is there, but it's going to cancel out on both of them. So I'm just going to show you one more. The rest are straightforward. It's just finding the antiderivatives, but I want to remind you of a problem like this. 0 to 3, there might be some problems that look like this. And you're like, okay, I find the antiderivative, but I can't find the antiderivative of this. I have no way. Remember, right now, all I know how to do is like power rules, trig functions. By the way, this one right here is for secant x, right? The derivative of secant is secant tangent. So they're straightforward. This is a power rule, but I can't find that antiderivative. So you still have to keep in mind that what does this mean? This means area under a curve. So the fundamental theorem of calculus is a great theorem. It's a great method, but it's only as good as we are, right? Like if we don't know how to find the antiderivative, not going to help us at all. We don't have a way to find this antiderivative. We will, ultimately. So we have to go back to the old ways, right? Draw a picture. So anything that you can't find the this is just a circle, by the way. Y squared plus x squared equals 9. Oops. So circle the radius at 3, and we're going from 0 to 3. So it's radius is 3, so 9 pi is the area, and we want a quarter of it, right? So 9 pi over 4. So sometimes we might throw that little trick in there at you, and that you can't find the antiderivative. You've got to keep in mind that this means area under a curve. We're going to start doing these problems, right? And then you're going to get answers. You're going to, I got it. We're going to get all these answers. And then at some point, you're going to forget what we're doing. But we are finding area under a curve. So if we can't do that using antiderivatives, we got to go back to some old ways, drawing pictures, things like that. Remember, we're pretty limited in terms of the ways we can find antiderivatives. So that's the fundamental theorem of calculus, clearly by its name, pretty important theorem. And we're going to learn a lot more about how to take antiderivatives as we move through the course.